Okay, thank you very much for the introduction. I'd also like to thank the representatives of the European Commission, the organizers of the FET conference, and also our local hosts here in Budapest for the opportunity today to talk about interdisciplinary research. And in particular, I'll be talking about my own approach to interdisciplinary research, which lies at the interface between evolutionary biology and robotics. As I'd like to talk about interdisciplinary work today, there'd probably be no better place to start than with a local scientific giant, John von Neumann. John von Neumann was arguably one of the last Renaissance men of the sciences. He made deep contributions to all the major branches of the sciences, but is also in many ways one of the first interdisciplinary researchers, in that his contributions to mathematics and the theory of computation were inspired by nature and in many ways inspired by the theory of self-replication. And in turn, his innovations in mathematics and computation gave back to biology. His contributions to what became known as game theory is now one of the cornerstones of modern mathematical biology. As we all know here, we're going to hear a lot more about interdisciplinary work, which is now very much in vogue. We'll hear much more about the flagship projects. I'm not quite sure if these numbers are exactly right, but we'll find out a little bit later. As an example of this in the United States, the National Science Foundation, the major funding body for basic research in the U.S., offers one of their largest awards, which is admittedly an order of magnitude smaller than the flagship awards. However, it's, I think, very indicative of the kind of interdisciplinary work going on in the U.S., that one of the first projects that was funded through the Expeditions in Computing Initiative was Harvard's project on robot bees. Although I'm not involved in that project, I think it sums up one of the reasons why robotics is interesting to so many of us, is that it challenges us to think about intelligence not just in terms of the brain, but to think about the body of the robot and how it makes use of its body, and animals and humans as well, to learn to become capable of adaptive behavior and eventually intelligent behavior. One of the cornerstones of intelligence is the ability to use our bodies to push against the world and observe how the world pushes back. And through that feedback loop between our bodies and our world provides the raw material on which learning then starts to occur. So there's a great intellectual motivation to robotics in that robots are the perfect tool for studying the idea of embodied cognition. Unlike with animals, we can arbitrarily change the bodies and brains of our robots and observe how those changes alter the kinds of behaviors that arise in animals, in humans, in robots. So obviously there's a great intellectual interest in robotics. Robots also have great practical use. In terms of industrial robotics, we've seen a complete revolution in manufacture over the last 150 years that actually started with Henry Ford, who formulated the idea of mass production. Mass production was the idea that the object being built should come to the worker and then to the next worker and so on. That led to a systematization of manufacture. And then many decades later, with the advent of industrial robotics, manufacture was automated. If you look at the way that we as societies build objects out of doors, like build buildings or roads or large civil infrastructure, we don't see the same kind of systematization followed by automation. If you look at a construction site, it's usually mostly people. You do see machines on construction sites, but these are not autonomous machines. They're being controlled by a person. I would argue that the disparity between these two processes can be summed up by a quotation that was attributed to the Greek philosopher Heraclitus, who said, "Man never enters the same river twice." If we want to try and deploy robotics in outdoor or unstructured environments, those robots have to continuously adapt their mode of operations to the continuously changing demands that these environments place on these machines. So we know how to build very sophisticated machines, but we still have a very hard time building adaptive machines. So I would argue that one of the main challenges in robotics is an intellectual challenge. What do we mean by adaptation? How does adaptation and intelligence arise in natural systems? And how can we take those inspirations and build them into our machines? If we could build adaptive machines, I think we'd see a similar systematization and automation in terms of outdoor construction. That would be particularly of use given the energy challenges that our societies face. There are a lot of different solutions that are being proposed, but one thing that they all share in common is the issues of scalability. If we want to really solve the energy challenges that we face, we're going to have to deploy energy harvesting devices over very large areas and in very great numbers. If we were to do that purely by hand or manually, it wouldn't make financial sense. So I think if we are able to start to build increasingly adaptive machines, we might be able to build some intelligence into the devices themselves so that they be able to adapt to their local environmental conditions. And in the very long term, if we could build adaptive mobile devices, they could very much help with the deployment and maintenance of these large-scale systems in the same way that industrial robots helped us to make manufacture on a large scale more cost-effective. We're not there yet, obviously. We don't yet know how to build sophisticated adaptive machines, but we do know of one system that's produced uncountable numbers of adaptive machines, and that's biological evolution. So from a naive computer scientist's point of view, we might think about natural selection as starting with a population of organisms in which there's some variation. Those organisms that are not well adapted to their local environment die off, and those that remain make modified random copies of themselves. And then by iterating through this algorithm often enough, we obtain a population of adapted organisms. In the 60s and 70s, both in Germany and the United States, a class of computer programs known as evolutionary algorithms were formulated, where now, instead of biological organisms, in the computer we have a population of solutions to a given problem, which I'm simply representing here as a string of numbers. We also give the computer the ability to measure the quality of any given solution. The computer then goes through and evaluates or tries out all of these solutions, and those that do better at solving the problem we've set for the computer remain, and those that don't do such a good job are deleted. We then make modified copies of the solutions that remain through simulations of mutation and sexual recombination. And again, by iterating through this process often enough, we often obtain automatically a solution to our given problem. If we take evolutionary algorithms and apply it to the problem of robotics, we obtain the subfield of robotics known as evolutionary robotics. This idea was independently formulated in Switzerland and the United Kingdom. Now the problem that we wish to solve is to automatically design a robot to perform an adaptive task. And like before, we're now starting with a random population of robots. Here the task is to lift round objects and move them off to the left, and to pick up square objects and move them off to the right. You can see that these initial random robots are not doing a very good job. But after about an hour on a standard PC, these days we start to see partially evolved solutions. These robots that are able to grasp the object for a little bit longer than the other solutions in the population are kept. The poorer solutions are deleted. And eventually, after about 8 hours on a standard PC, we automatically evolve a solution to our problem. So if you break open this robot and try and understand its brain or its controller, it's very difficult to understand. Evolution has found a solution that works for us automatically. There are a large number of these experiments that are out there now. Obviously, evolutionary robotics and evolutionary algorithms are a great simplification of biological evolution. One of the main simplifications here is that biological evolution obviously does not gradually change the nervous systems of animals over time while leaving their body plans untouched. evolution shapes the bodies and brains of evolving animals simultaneously. So in the mid-90s, Carl Sims in the United States proposed an expanded evolutionary robotics experiment where now he had a digital game preserve. He had a whole bunch of virtual creatures in a supercomputer at that time that were evolving, in this case, the ability to locomote. Since that time, in some of my PhD work, we expanded this work to more complex robots and more complex evolutionary algorithms. Hod Lipson, then at Brandeis University, now at Cornell University, created another evolutionary system where he evolved these virtual creatures in simulation, and then attached his simulator to a 3D printer and was able to automatically manufacture a physical version of this robot. And there have been a number of EU and US projects since then. However, there's relatively few examples of these kinds of systems out there because they're very difficult to build. It takes a long time to program such an evolutionary system. And so you might ask yourself, why bother? Why should we go about trying to evolve both the bodies and brains of these virtual creatures simultaneously? The reason why is it's very difficult to look at an animal or a human body plan and try and take inspiration from that and build into a robot the infinite number of physiological details we see in the animal of interest or the human in interest. It turns out to be a very difficult thing to do. So instead, we want to try and automate this process and allow evolution to discover the subtleties of physiology that help our robots to perform the behavior of interest. Just as an example of this was an experiment where we're just evolving three-dimensional shapes. There's no brain here, there's just a three-dimensional shape, and the task that we set the computer was to evolve a shape that allows this object to roll as far as possible, and there's some subtleties in terms of the curvature of this object and the mass distribution in this object that allow it to roll a long distance forward. So evolution, artificial evolution, is able to exploit or discover these subtleties of shape, of mass distribution, of material properties. In fact, tomorrow there'll be a workshop on soft robotics. Advances in materials engineering and materials science provides new opportunities for artificial evolution to automatically design new kinds of robots for us. Just continuing on with this theme of robot shapes, in some most recent work, we've evolved some virtual creatures that tend to have fractal body plans. So fractals are a pattern that we see throughout nature where we have some particular structural motif like a spiral, and that structural motif is copied at smaller and smaller scales. If we have a look at the robot in the top left here, we can see that there are particular structural motifs that are copied at smaller and smaller body plans. It turns out that these fractal robots tend to be more evolvable than a similar system that is not able to discover fractal body plans. This issue of evolvability, or how easy it is to evolve increasingly sophisticated machines, will be the topic of a workshop later this afternoon. So I've shown you a little bit about how artificial evolution can be used to simultaneously shape bodies and brains of robots together, and I've shown you how we can use this to design virtual robots in simulation. We can then manufacture physical versions of these virtual robots, and we can then deploy our physical machine out into unstructured environments and hope that that physical machine can continuously adapt to the changing demands of unstructured environments. And it turns out that evolution can help us with this third stage of robotics, with this stage of deployment. A few years ago, together with my colleagues Hod Lipson and Victor Zykov, we published a paper in Science where we showed evolution helping us to create what we call resilient machines. In a resilient machine, we start with the physical robot. It performs a number of actions, and it obtains some experiences from its environment. It then uses those experiences to discover a body image. It's able to evolve an understanding of its own body, In this case, our resilient machine has discovered that it has 4 legs, each leg has 2 parts, and so on. And by evolving this body image, our robot is now able to better understand the opportunities and limitations of its own body. In this case, we've posed a task for our physical robot to accomplish, which is to move from the left side of the table to the right side of the table. So before trying anything in reality, our robot introspects. It uses its self-model or its body image to come up with a way of moving. In this case, it's using a second evolutionary algorithm to search the space of all possible actions. It finds this particular way of moving and then tries it out in reality. And more often than not, what it thought would work tends to work in reality. So using this evolutionary algorithm, and by connecting a simulator to a physical robot, we can enable this autonomous machine to teach itself new behaviors. In this case, our robot has taught itself to walk. However, as I mentioned, we're interested in adaptive machines, so we then present the robot with an unanticipated situation, which is that we separate part of the robot's right leg. You can actually see the motor is still dangling here in the background. Our robot has no equivalent of pain receptors. It doesn't know that this physical damage has occurred. Our robot doesn't have a camera on board. It can't see the damage that's occurred. All our robot knows is that something has changed, and its previous mode of operation is no longer appropriate. So the robot goes back to the introspection phase and uses artificial evolution to come up with a new description of its own body. And in this case, our 4-legged robot comes to understand that it's now a 3.5-legged robot. And it realizes that in this new circumstance, its previous way of walking doesn't work. So it evolves a new, completely different way of walking. And once it's discovered or evolved this new gait, it tries it out in reality. And although not the most graceful mode of locomotion you've ever seen, it's enough for our robot to get the job done. It doesn't have the same efficiency or speed that it did before, but this is arguably one of the first instances of an autonomous machine that can teach itself a behavior of interest. It experiences some unanticipated situation, it diagnoses the problem, and comes up with a way to recover. So now evolution is helping us not with the original design of the robot, but it's helping the robot to be more adaptive in these physical environments. So that's the first lesson that evolution has to teach us, which is that evolution allows us to gradually shape or improve all subsystems of the technology simultaneously. In the case of robotic technology, we're trying to optimize the body plan of the robot, the sensor distribution, the motor distribution, along with the neural controller of our robot. But evolution has other lessons to teach engineers and roboticists in particular. The first one is that biological evolution tends to exploit the fact that animals change over many different time scales. Over the slowest time scale, we have phylogenetic or evolutionary change, where evolution is acting to gradually improve the body and brain of the animal so that it's better adapted to its environment. But within these evolving populations, any one organism experiences profound change to its body and brain over its lifetime, and evolution is shaping that developmental change over its lifetime. This is known as the evolution of development, or evo-devo. At the shortest time scales, higher animals and humans learn over minutes and hours and days and weeks and months to be able to exhibit increasingly sophisticated behaviors that play out over minutes or seconds. So biological evolution is orchestrating all of this different change at different time scales. And that poses a question to roboticists. Typically, we build the machine of the robot, and then the robot's body does not change as the robot performs its task, with the exception of physical damage that you just saw. So in some of our most recent work, we published a paper in PNAS where we showed that these 3 time scales, evolutionary, development, and the here and now timescale are actually useful to us as engineers and roboticists, and I'll show you why that's the case in a moment. First, I'll show you another one of our virtual creatures. This one has a lifetime of about 5 seconds. The goal here is for our robot to go from the origin to this target object that it can sense. But you'll notice that this robot begins as a legless, segmented robot, and then as it's behaving, it gradually grows legs, and these legs become increasingly vertical, so that at the end of its 5-second lifetime, it's actually an upright, legged robot. So we've got a robot that's experiencing developmental change. Its body is changing over its lifetime. We then embed this system within an evolutionary algorithm where we start with a population of these robots that are going from this infant legless to this adult legged form. They evolve the ability to find and move toward the target object. But then later in evolution, the descendant robots gradually lose this infant form so that in the last few generations, all of the robots start in this upright legged form and maintain that legged form throughout their lifetime. We compared this against a control experiment where the robots did not experience any change during their lifetime. And it turns out that in the experimental case here, we were able to evolve successful robots faster and transform them or transfer them to simple physical machines. Here we're just prototyping them with some Lego robots. It turns out that we're able to evolve controllers faster compared to the control case, and these controllers are more robust. We're better able to transfer them to the physical robot because these controllers evolved over lots of different kinds of robots with different body plans. So an observation that we take from biology, which is that animals change over many different timescales, and build that into our robotic system actually gives us an engineering advantage. We can continuously design behaviors for our robots faster, and those solutions are more robust. So that's the second lesson that evolution has to teach us. The third and final lesson that I'd like to talk about today is that biological evolution always relies on populations. So as engineers and technologists and roboticists, we're challenged to think about populations of technology, not just focusing on a single piece of technology and trying to improve it. So here, as a starting point, we've got a single human user that's running an evolutionary robotics experiment on their PC. Here they're trying to evolve coordinated motion, which is the ability of a swarm of robots to move in unison. You can see that they're not doing a very good job yet. If we give evolution a little bit longer, hopefully it will improve the solution. But we now take this idea of populations and turn it back on our human users. So in our most recent work, which we refer to as the gamification of robotics, we're trying to take the problem of robotics and gamify it, or crowdsource it out to a population of human users. So now we've got populations of virtual robots and populations of human users. We started with the first user who did some evolution and evolved these robots for a few hours or a few days, and then broadcast this partial solution to their peers over their social network. And this partial solution was picked up by one of their peers, user 2. User 2 then contributes some more local computation to the problem, broadcasts that on her social network to her next friend, and so on and so forth. So now we have a form of implicit collaboration among these users where they're jointly contributing computation to the problem of robotics. This idea of gamification is a growing trend on the web where we take a hard problem like a scientific experiment or a distributed search task and turn it into a game. We gamify it. And in the successful gamifications you see out on the web, there's a very careful balance between collaboration in these human groups and also competition between the groups. So when we gamify robotics, as you just saw, we have members of a social network that are jointly contributing computation to trying to evolve the best robots that they can. and they coalesce as a team and compete against another team of human users who are also trying to evolve the best robots that they can. And the game might be which team can produce coordinated motion among robots in the shortest period of time. There's some similar approaches to this, not in robotics, but in some other scientific fields. But one of the main remaining limitations of this approach is that our users are still mostly passive. They're contributing computation to the problem, but not really contributing creatively to the problem. So in our most recent work, we've tried to unlock the creative potential of the users and allow them to reach into the simulation and design a task environment that favors a particular kind of behavior. So just to finish up here, let me walk you through one example of how this works. Let's imagine that we have 3 human users, user 1, user 2, and user 3. User 1 is inspired by the fast locomotion observed in the large cats and wants to try and design a task environment in which an evolutionary algorithm will select for fast locomotion. They do that by dragging the target object far from the robot and indicating that the robot should run as quickly as possible from the origin to this point next to the target object. User 2, on the other hand, is inspired by ballistic motion, which is a class of behaviors like jumping or throwing an object very precisely. Ballistic motion compared to locomotion has its own challenges, which is that you see a very large burst of activity to the muscles or motors in the case of a robot, and after that burst has occurred, the animal or the robot has no ability to fine-tune the behavior. So now user 2 is going to define, using the same application, a different task environment so that evolution will now favor jumping. So we see user 2 here creating a step, and the robot is going to have to jump up onto this step. User 3, on the other hand, is interested in brachiation, or the ability of the primates to swing from handhold to handhold. This behavior also has its own unique opportunities and challenges, which is exploitation of the weight of the animal, exploiting momentum, and requires very careful timing for hand grasping and hand release. So now, in order for evolution to favor brachiation, user 3 now is going to create a virtual beam, and the robot is going to have to, as it's falling, grab onto the beam, swing under the beam, and get as close as it can to the target object again. So now that our 3 users have creatively contributed to the problem, they can sit back and contribute computationally, where user 1 starts to evolve locomotion. We definitely don't have anything approaching the fast locomotion of the large cats yet. But again, we're on our way. User 2 has been able to evolve a primitive form of ballistic motion, and finally user 3 has discovered brachiation. Again, not perfect, but on the way. So now our 3 users have created these environments, they've started the evolutionary process, and they broadcast their partial solutions across their social network, and these solutions are picked up by users 4, 5, and 6. And now users 4, 5, and 6 expand in the simulation these task environments. So now we can see the users here creating multiple task environments. So they're going to try and improve on the solutions of their peers. In the left here, the user is defining a number of placements of the target object so that the robot has to move towards the target object no matter where it is. In the second case here, the user has decided to create a number of steps, and the robot is going to have to hop from one step to the next. User 3 has created multiple beams so that as the robot starts, it has to detect where the target object is, grab onto the correct beam, and swing in the correct direction. And now users 4, 5, and 6 restart the evolutionary system, and the first thing users 4, 5, and 6 realize is that this is a much more challenging task for evolution. But despite that, after about a few minutes on a standard PC, our users start to evolve partial solutions to the problem. So that's an example now of trying to take this idea from evolution about populations and apply it back to large groups of human users so they can contribute creatively and computationally to the challenges of evolutionary robotics. So in closing then, I've tried to show you a number of examples from my own work and other projects here in the EU and the US that look at robotics through the lens of embodied cognition. Roboticists are challenged to think not just about the brains of animals, but also about their bodies, how animals push against the world and observe how the world pushes back. So in many ways, we try and learn as roboticists how the body shapes the way that animals and humans think and build that into our machines. More specifically, I've talked today about the way in which evolution shapes the way that roboticists think. And we've instantiated in our own work 3 particular phenomena we see in naturally evolving populations, which is that evolution optimizes all subsystems of organisms simultaneously and challenges us to try and do the same with robotic technology. Evolution exploits change on multiple timescales, evolutionary timescale, the lifetime of a single animal or robot, and also the second-to-second behavioral competencies of an animal or robot. And finally, evolution always operates on populations. So can we combine the best of brute computation in populations of computers and populations of robots and marry that to populations of creative human individuals that contribute creatively and computationally to the task? Obviously, given the time limitations, I've only been able to touch on these various projects. I'll be here throughout the meeting, so if people would like to talk about any of these projects in more detail, I'd be happy to. There are copies of my papers online here. I'd like to acknowledge my PhD student, Josh Auerbach, who contributed some of the videos. And finally, I'd like to thank my funding agencies for sponsoring my research. So I'll stop there. Thanks very much, and I'll take questions if there's time.
Thank you, Josh, for getting Fet11 off to such a brilliant, stimulating start. I'm afraid there isn't time for questions from the floor, but I'm going to ask you one question, which I hope will help people understand what you're doing. And that is, tell us a bit more about how you get from these computer simulations, whether they're developed on social networks or by individual scientists, to physical robots moving around. I mean, you mentioned Hod Lipson at Cornell doing a 3D printing, but that's not going to produce the sort of thing that can leap around on stage. How do you get from the computer to the physical object easily?
So I think that's a very good question. You mentioned 3D printers. There's a whole field of rapid fabrication and prototyping technologies that are emerging. There's a lot of interesting work going on in materials engineering and materials science, looking at how we can automatically manufacture in a very cost-effective way these virtual robots. So I think there's lots of opportunities there, but it's still a technology that's in its infancy.
So to some extent, you'll still have to build the things off the computer.
For the moment, yes.
Okay. Well, thank you again, Josh. I should repeat that he's going to be around, and in particular, he'll be around in the scientific cafe after lunch, so there'll be plenty of opportunities to put your own questions to him. Thank you. Thank you.